So if we go back and bring up these these two series from the last lecture, this is ne to the minus n over 2 as n goes from 1 to infinity, and this one was 1 over 2n plus 1 as n goes from 1 to infinity. And so if we look at these in terms of finding the area under the curve of each one of these two equivalent, of each one of these functions, rewriting the series in function notation, I think it's kind of an interesting phenomenon that really as we integrate this function, it goes to a finite value, 3.632 roughly. And as we integrate this function, that pinches off, like this one does, even pinches off far more dramatically, it looks like, at least early on. We find that this area is infinite. Even though this looks early on to be a lot smaller, what we have to really pay attention to is what happens out here. And as we can see that once we get way out here beyond A8 and A9 and A10, this pinching here is less drastic or less severe than the pinching here. You can see this already kind of blends in with the axis after maybe the 9th or 10th term. This doesn't blend into the axis until way beyond the page, and so, or way beyond the screenshot. So this pinching is less severe, and it's all these little pieces, these little areas, these rectangles that I was drawing in blue here that are too small to draw here. It's all of these tiny, tiny rectangles that have this massive cumulative effect to make this area become infinite. And so we have to ask ourselves, when we deal with these series here that have this pinching off effect, when is the pinching off severe enough to cause a finite area? And as we have in this case right here, here's the finite area, here's the convergent series. This is an infinite area, this is a divergent series. And really, the truth lies in the fact that we have to look way out here at these terms, way far in the series. We can't really, we don't really need to be concerning ourselves with what happens early on in the series. That can be very deceptive. It's this cumulative effect of summing these rectangles way out, summing these terms, so to speak, way out at the 10,000th and the 20,000th and the 50 millionth term, that we really see this true effect of accumulation. So this ends up to diverge, even though early on it looks like it pinches more severely than this. This ends up converging because later on in the series it ends up being a more severe pinching or asymptotic behavior with the horizontal axis. And so the activity we're going to go into is going to take a series that is non-increasing and that pinches off like this, and we're going to look at a family of series that do just that, and we're going to find this transition point as to where it goes from infinite area to finite area. This first series is 1 over n to the 1/4, and we want to graph the first 10 terms of this series, and we're going to do that. We're going to graph these first 10 terms and show those terms as dots. And the quickest way to do that really is with lists in your graphing calculator. So if I come over here and go ahead and edit list 1 and go ahead and put in the first 10 terms here, And then we can come up to the top of the list here and go into the header and then set up an equation here for list 2. So that's going to be 1 divided by the quantity x to the 0.25 power, and oops, not x to the 0.25 power, but list 1 to the 0.25 power. And we can get the values there. So we start at 1, the value is 1 over 1 is 1, and then 0.84, 0.75, 0.7. So we see this non-increasing characteristic in each one of the values here. And then if we go to our graph, we have, and go to stat plot, we can go ahead and get a graph of this. And list 1 is on the x, that's 1 through 10. List 2 is 1 over n to the 1/4 power. And we will go ahead then and zoom stat. And there are those 10 values. And so if we do a minimum, an x minimum of 0 and a y minimum of 0, I think we'll be able to see the axes. There we go. So there's the axes. So if we then go ahead and get that graph on here, we can, I think I should be able to stretch that so that it matches up with, there we go, matches up with our axes. So there's our 10 points graphed. And so this is then, you know, these are each individual term, and if we rewrite then that as a function, we're going to look at rewriting this as a function. We're looking at 1 over x to the 1/4 power, and then if we find it easier to integrate without the fraction here, we can write this as x to the -1/4 power. And then we can go ahead and do the integral test. So if we look at this, then we have performing the integral test. What we're really looking at is the area here underneath the curve. And so if we set up to find the area under the curve here, we can go ahead then and do that integral test from 1 to infinity of x to the -1/4 dx. And integrating that, increasing this power by 1 would get us 3/4, multiplying that by the reciprocal 4/3 x to the 3/4. And that we're going to evaluate that from 1 to infinity, and really that's improper, so really what we're looking at is the limit as b goes to infinity of 4 over 3 x to the 3/4 power from 1 to b. And so as we evaluate that, just talking about the limit as b goes to infinity of 4/3 b to the 3/4 minus 4/3 1 to the 3/4 power. And as b goes to infinity, then we're looking at an infinite area. And so that being the case, then we have a, since the limit goes to infinity, this series diverges because of the integral test. And so we talk about this characteristic of pinching off as this non-increasing series pinches off against the axis here. is that pinching drastic enough to cause this area to become finite? And the idea is that it's not drastic enough for this area to become finite. And so if we look at then the Riemann sum, so if we kind of don't focus on the area so much, if we don't focus on the area so much, so let me go into properties here and make this a little transparent, so that we can kind of make that disappear a little bit. If we use a pencil here, or excuse me, if we lightly sketch the appropriate Riemann sum representing each term of the sequence. So with a Riemann sum, we're talking about setting up rectangles here. So we're going to set up a rectangle with this height and a width of 1, so that a sub 1 rectangle is going to look like that. And the a sub 2 rectangle is going to look like that. And the a sub 3 rectangle is going to look like that, and the 4 rectangle is going to look like that. So as we're calculating the areas of all these rectangles and adding those up, that is the physical sum of the infinite series, which would be just adding up all the terms or all the y values of that rectangle. And so the area, the blue area being infinite in value, we really have no determination as to whether or not all these rectangles add up to infinity or something else. So we say that the limit does not exist. As we next look at 1 over n to the 1/3 power, so all we're doing really is changing this power here. Then we're going to go through the same idea of graphing the first 10 terms for that sequence. So if we go back to our list here, and we'll keep our same first 10 digits, we'll come up here and we'll go ahead and redefine that to be 1 divided by the quantity x raised to the 1/3 power. So I'll put that in brackets. 1 divided by 3. And oops, I think I did the same thing. That should be an L1, not an X. So I'll go back there and put in an L1, not an X. And I don't have my caret. So insert a caret. There we go, L1 to the 1/3 power. Then I get my new values for that. And if I graph that, we're looking at that graph for the non-increasing function. And so if I would plot that on the axis, and scale it so that it's appropriately sized, then here is n to the 1/3 power. And so if we go through again and take a look at basically this being a function, so we're talking about 1 over x to the 1/3, and performing the integral test on this as if it were a continuous function, then that would just be integrating x to the minus 1/3. And so we can do that and take a limit as b approaches infinity of 1 to b x to the minus 1/3 power. Yeah, make that a little nicer looking. There we go. 1 to b of x to the minus 1/3 power dx. And so when we integrate this, bumping this up to about by 1 is 2/3, so we're multiplying by the reciprocal. So we have 3/2 x to the 2/3 power. evaluated from 1 to b, and if we evaluate that from 1 to b, we can see that when we take 2/3 times b to the 2/3, or 3/2 times b to the 2/3 power minus 3/2 times 1 to the 2/3 power. 3/2 times b to the 2/3 power as b goes to infinity is just, again, infinity. And so we're looking at this, this area again under the curve is still infinite even as we're changing this power here. And so we still know that when we have this power, we still have infinitely large area, and so we have then a series that also diverges. So as we are kind of trying to figure out when we transition from this being a divergent series, we'll just go ahead and keep changing the value of the power here. And so we're looking at n to the half power, so I'm going to go ahead and come up here to the top of list 2 and say this is 1 divided by the quantity list 1 to the half power, which is 0.5, or the square root of list 1, however you want to write that. And so we get new values here for each term, and when we graph that, we get that graph. So these all have the basic same shape, but there's definitely something happening with each one of these graphs. They're changing slightly, and we'll get into that change as we kind of work our way through here. And so if I go ahead and scale this up so that it kind of matches the scale on my graph a little bit, pretty close. There we go. Then again, as we integrate this one, so we break this in function notation, 1 over x to the half, or 1 over the square root of x. And I'll just write it as negative exponent just to help the integration. And so as we're looking at this and determining the area under this curve, we can write the limit as x approaches infinity, and from 1 to infinity of x to the negative 1/2 power dx. So as we integrate this, bump this up by 1, it's positive 1/2 multiplied by the reciprocal, which is 2. Excuse me, not x infinity, as b approaches infinity. This should be infinity. As b approaches infinity. So we're looking at 2x to the 1/2 power from 1 to b. And so we're talking about the limit as b goes to infinity of 2b to the 1/2 minus 1 to the 1/2 is 1, so minus 2. And so as we look at that and plug in infinity, we still get an infinite value here. So the value of this area is still infinity, and so we still have a divergent series here. So let's go ahead and change the power again. So now let's go ahead and make this a power of 1. So we just have 1 over n. And so graphing that, putting that in our list, we're going to have going to come up here into my list header again, 1, and call that 1 divided by x, and get some, I did it again, not 1 divided by x, but 1 divided by list 1. There we go. And so we're going to get those values. And so our graph is going to look like this. And you might kind of already start to see what's happening with this graph here as we are changing these powers. I think that one is a pretty noticeable difference from the graph before. But if you notice, we're always focusing on this pinching off against the x-axis here. and whether or not that pinching off is going to get us finite area. And so if we look at this then, there we go, and write this in function notation, that would be, the function notation would be 1 over x. So we're looking at integrating 1 over x here, and there we go. And we could write that as a negative exponent, but I think integrating 1 over x is pretty easy. So we're talking about the limit as b approaches infinity of 1 to b of 1 over x dx. And we know that as the natural log. So we have a limit here as b goes to infinity of the natural log of the absolute value of x from 1 to b. And so as we plug in the upper and lower bounds here, we've got the natural log of the absolute value of b minus the natural log of 1, which is 0. And of course, as b goes to infinity, the natural log goes to infinity. So even with 1 over x, even as we transition from a fractional power to a whole, an integer power, we still have a divergent area. We still have infinite area under this curve here. And if we still have, if this area here is still infinite, then we still have a divergent series according to the integral test. So we've been through powers of n that basically go from pretty small all the way up to 1, so really powers that were trapped between 0 and 1 so far. And if we kind of take a look at, just kind of review those 4 that we've already done, here is n to the minus 1/4, here is minus 1/3, minus 1/2, minus 1. So you can see that as I flip through these, that pinching occurring. There it's pretty far away from the x-axis, and it's getting continually closer and closer and closer. And so we see that pinching off becoming more dramatic. And so the real question is when is the pinching off dramatic enough to cause this value to be finite? So we're just going to continue with the pattern here and keep increasing this power that's written in the denominator here. So now we have 1 over n squared. So we'll go ahead and come back up here to our list header and type in the expression 1 divided by list 1 squared and get some new values here. So there is 1 over 1 squared, 1 over 2 squared, 1 over 3 squared, 1 over 4 squared, etc. And as we look at that graph, we can see that that pinching is even becoming more dramatic. So if we kind of size this up here to fit on our grid, there we go. So now as we look at this in function notation, as we prepare to do the integral test, we can see that we're really getting dramatically tight here against the horizontal axis. So writing this in function notation, we're going to be integrating here 1 over x squared, which is x to the minus 2 power, if you want to call it that. And so we're looking at integrating from 1 to infinity. I'll leave it as x to the minus 2 power dx. And so as we are evaluating this, using the power rule, we bump this up by 1. That's a -1. The reciprocal of that is still a -1. So we're going to get the limit as b goes to infinity of -1 x to the -1 from 0 to b, or not 0, from 1 to b. And so putting in the limits now, the limit as b goes to infinity is, I'm going to write this, since this is x to the minus 1, I'm going to write it as 1 over x, so it's minus 1 over b to the 1 power. I'm not going to write the power though. Minus a negative 1 over 1, again to the 1 power, but I won't write that first power. And so now when we stick in, if you notice back here, we always had b in the numerator. Now we've come to having b in the denominator. And so now as we evaluate this as b goes to infinity, we have 1 over infinity, which is now 0. And so this limit then is 0 minus a negative 1, which ends up being 1. So we know the area under this curve is 1. It's a finite value. So now we have a situation where this series converges to some value x, or to some value, excuse me, that is somewhere in the neighborhood of 1, but we don't know what the exact value is. But we have definitely a finite limit. And so now we've got convergence. And so if we continue this process here and look at higher powers of n, like n to the 3rd power, we can see that if we go back to our list here and type in n to the 5th power, so we're talking about 1 divided by x to the, not x, 1 divided by list 1 to the 5th power. You see how dramatically small these things get. And so if you can't even really see the dots there. There's 1, 1, and then everything else seems to just disappear right up against the axis, so that pinching off gets far, far more dramatic as we see that power grow bigger than 1. And so, and this would even be tough to sketch in here, because that pinching off is so dramatic. So we're right up against that axis. So we're talking about a function of 1 over x cubed, and cubed isn't such a big power. We have powers of 6, 7, 8, 9, and you can probably speculate as to what happens with this pinching off phenomenon. But we're integrating x to the minus 1/3, so we're talking about taking a limit as b approaches infinity from 1 to b of x to the minus 3rd dx. And so bumping this up is a minus 2. The reciprocal of a minus 2 is negative 1/2. So we're talking about the limit as b approaches infinity of negative 1/2 x to the minus 2 from 1 to b. And so evaluating that limit, we're talking about, this is negative 1 over 2x squared. So we have negative 1 over 2b squared minus a negative 1 over 2 times 1 squared, which is just 2. And so as we put infinity here, this goes to 0 minus a negative 1/2. So we get an area under the curve here of 1/2. And so, again, that's finite, so we get a convergent series here. And so if we bump this up to 4, you might be able to speculate what happens here. We're going to get even a smaller area. And since x cubed converged, this is going to have to converge if our area is continually getting smaller and smaller. So if we kind of summarize what we found here relative to 0, we had powers of 1/4, 1/3, 1/2, 1, 2, 3, and 4. And so we're talking about a quarter, so we had a general pattern of 1 over n to some sort of power, and we had powers equal to 1/4, 1/3, 1/2, 1, 2, 3, and 4. So if we graphed these values of the power on the number line, we'd kind of be like right here, and right here, and right here, and here. There's 2, there's 3, there's 4. And so where did we have that transition from being infinite area to being finite area? We had that transition right here. So from a power of 1 back into here, we had a divergent or infinite area, so a divergent series, and then anything bigger than 1, so all of these were divergent, and then anything bigger than 1, we had convergent. So these were all convergent. And we saw that because we had a finite area. Just erase this here. We had a finite area when we performed the integral test. And so with these findings then, we can see this pattern start to emerge. And this pattern is what's known as the P-series test. And the P-series test is literally taking a series that has the form of 1 over n to a power and just looking at the power, looking at the value of the power. To make a determination as to whether or not the series converges or diverges. And so what they're doing now is, all we have to do is look at the value of the power as long as the series is in that form, then we can really bypass the use of the integral test altogether for these type of non-increasing functions.